to XS3 core converter. Now tell me, given a BCD number, how to convert to XS3 code? First, before going for conversion, you must know the process. How? Given a BCD number, how to convert that to XS3 code? Let us suppose I have given 6 BCD number. How to convert that to XS3 code? 6 plus
3.
3. So if you go for 6 plus 3, what will be getting? What will
9.
be? Yes. So the 6 representation in BCD, if you want to represent in XS3 code, it is 9. Okay. Similarly, if it is 0, the XS3 code will be what?
3.
Means 3. Similarly, if it is 2, the XS3 code will be 2 plus 3, it is
5.
5. Okay. So this is your XS3 code. First, you must, before going for conversion, you must know the process. Given a BCD number, how to convert to XS3 code is, we need to add for BCD number plus 3 so that you will be generating an XS3 code. First question that I want to ask for you all is whether this XS3 code is weighted or unweighted code. Is XS3 code is weighted or?
Non-weighted.
Yes, it is non-weighted code. Okay. Next, XS3 code is also called as?
Self-complementing.
Yes, good. So, XS3 code is a non-weighted code and XS3 code is a self-complement code. Okay. So, what we are doing, given a BCD number, we need to design a combinational circuit. So, this is your combinational circuit. In this, you will be combinational circuit is what? Combinational circuit is a combination of all logic gates so that you will be having a specified output. So, BCD is represented in how many bits, man? B6 is represented with BCD 6. Where is this? BCD 6 is represented in BCD. How many bits?
4 bits.
Yes, it is 4 bits. So, the input for this will be 4 bits. The input for this will be 4 bits, which is BCD number, and the output from this 4 bits will be XS3 code. The output from this is XS3 code. Okay. Now what is this combinational circuit means? After finding your k maps, the expression that you got, if you complete the logical expression, then that logical expression will be placed here, so that given an input BCD, you will be generating an output XS3 code. Okay. So now let me start with the truth table. So just now I mentioned input BCD is represented with 4 bits. So the input combination is 4 bits. So let me start with decimal. So let me start with decimal number 0, 1, 2, 3, 4 until decimal until how many? Until 9. Why? Because BCD is valid until 0 to
9.
yes. So BCD is the range is from 0 to 9 as it is. Why? Because it is binary coded decimal. So decimal base is 10. So 10 is represented from 0 to 9. So until 0 to 9 it is valid. So 0, 1, 2, 3, 5, 6, 7, 8, 9. Okay, this is decimal. And the input we are taking BCD. So you will be having BCD as one input and the other one is decimal XS3. And the other one is XS3. XS3. Okay. Now 0 is represented in BCD with 4 bits. BCD means 28421 means 0 0 0 0, and next one is represented as 0 0 0 1, 2 as 0 0 1 0, 3 as 0 0 1 1, 4 0 1 0 0, 5 0 1 0 1, 6 0 1 1 0. Answer, repeat. 8 1 9
Triple zero.
1001. Okay, now XS3 code. XS3 code, here it is 0, 0 plus 3. It is what I need to write here? 0000 or 0011?
0011.
0011. Next, here we have 1. 1 plus 3 is 4. So 4 is represented as 01.
Double zero.
Next, here we have 2. So 2 plus 3, 5. So 5 is represented as
0
0.
1 0 1.
Next, here we have 3. 3 plus 3, 6. 6 is represented as
0 1 1 0.
yes. Next, here we have 4. 4 plus 3, 7. So it is represented as 0,
Triple 1.
1, 111. Next, it follows sequence 3, 4, 5, 6, 7. Next is 5 plus 3, 8. Next, 6 plus 3, 9. Next, 10. Until 9 plus 3, until 3 to
12.
until 3 to 12. Yes, until 3 to 12. 1 0 1 1 1 1 0 0. So this is your truth table given a BCD, how to convert to XS3 code, the same one which I want to show in this. Okay, so this is a 1 0 to 9, and this is your BCD representation, and this is your XS3 representation. Now next step is finding the expression for W, X, Y, Z using
K-maps.
K-map. How many variable K-map will you select?
4.
Yes, 4 variable K-map. Okay. So let me take 4 variable K-map. Let me take 4 variable K-map. Now let me take the inputs what we have considered in this example. The inputs that we considered here is A, B, C, D, and the outputs that we considered is W, X, Y, Z. Okay, so I need to start my K-map with W, next with X, Y, and Z. Okay, so let me start with W. So let me start with W. The inputs that we selected is what inputs, ma'am? A,
A, B, C,
B,
D.
C, D, and W, X, Y, Z as input. So let me calculate for W. Let me calculate for W. So you'll be getting 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Tell me the expression for W. Sum of M equals to. Hmm. Hmm. Tell me the expression for W, ma'am. Sum of M equals to 5.
5, 6, 7, 8, 9.
Yes, 5, 6, 7, 8, 9. Let me complete for all, then we can go directly for K maps. So W equals to sum of M 5, 6, 7, 8, 9. And for X, for X, for X,
1, 2, 3, 4, and 9.
1, 2, 3, 4, and 9. And next for Y. Others also please respond, ma'am. For Y, 0,
3 4 7 8.
3, 4, 7, 8. Okay, for Z, for Z,
All even numbers.
0.
0, 2, 4, 6, 8. Yes? Yes, 0, 2, 4, 6, 8. So that we identify. And one thing that everyone has to consider in this case is, as BCD is represented, listen all of you, as BCD is represented with 4 bits, if it is 4 bits, 2 power 4, we will be getting how many combinations from 0 to 0 to 15. But we stopped until 9. Why? Because the valid BCD numbers are from 0 to 9. If it is 10, if you want to represent 10, 11, 12, 13, 14, 15, what happens? You will be representing with 4 bits as 1010, 1011, 1100. But what happens? It will become invalid. It is invalid BCD. Means if input is given as an invalid, if there is no corresponding output generated, then if an invalid input is given, the output will be don't care. If an invalid input is given, then the output will be don't care. So here, whenever you are constructing a 4 variable K map for these conditions, for 10, 11, 12, 13, 14, 15, the outputs for those will be don't care conditions. Why? Because if there is an input, we know that for this input the corresponding XS3 code is 0011. But for invalid BCD, there is no such output for that. So we'll be considering as don't care conditions. So if you consider those as don't care conditions while constructing, we can utilize those don't care don't cares for simplification of our expressions, as we already discussed K map with don't cares, right? So in this case, 10, 11, 12, 13, 14, 15 will be considered as don't care. Okay, so let me start. So this is your expression. Now tell me, for W, it is summation M of
5, 6, 7, 8, 9.
5, 6, 7, 8, 9. So let me write 5. Where will be 5? 0, 1, 0, 1. This is your 5. Next 0, 1, 1, 0. This is your 6. 0, 1, 1, 1. 0, triple 1 is your 7. 0, 1, 0, 0 is your 8. 0, 1, 0, 1 is your 9. Okay. Next, I have represented 5, 6, 7, 8. Next is what? Don't care. So also I need to mention don't care. So where is 10? 1, 0, 1, 0. This is your 10. Don't care. 1, 0, 1, 1. 1, 0, 1, 1 is what? 11, which is also a don't care. Next, 1, 1, 0, 0, 12, don't care. 13, don't care. 14, don't care. 15, don't care. So these are all don't cares. So these are all don't cares. Now, how to group? I will ask how to group. Think about the maximum. So, where is this cursor? I can group this one as one group. Next, the other groups, how to group? The other, how to group, ma? Tell me, this one as one group, this one as the other group. Tell me the expression for first group. W equals to, tell me the expression for W equals to for group 1. For group 1, all these will be cancelled, all this will be cancelled, and the answer that you will get is
A.
A. Okay, plus, tell me the expression for 2, second group. In this 2, you will be getting B, and from this above,
BC.
BC plus, again from this you will be getting, for this group you will be getting B, and above this 2,
D.
D. This is your expression for W. So even you can write this as, A plus B, C plus D. Okay, so can I write this? Yes. So I'm taking B as common and I'm writing C plus D. Okay, A plus C plus D. So this is the expression for W. Note down in your notes. I will ask you. Next, let me go for the next expression output called X. Okay. So new. I will erase this. I will take a new one. So I need to calculate the output expression for X now. So this is your K map. Next, the inputs are A, B, C, D, and it is 0, 0, 0, 1, 1, 1, 1, 0. Here also it is 0, 0, 0, 1, 1, 1, 1, 0. So next, tell me the for X, ma. Where is this cross?
1, 2, 3, 4, 9.
1, 2,
3,
3,
4, 9.
4, 9. Okay. So in this place, I need to keep 1. So it is 1. 0, 0, 0, 1 is 1. Next 0, 0, 1, 0 is 2. Next this is 3. Next it is 4. Next 1, 0, 0, 1 is 9. Okay. So remaining cases I need to keep don't care for position 10, 11, 12, 13, 14, 15. These are don't cares. Okay. So now, is this correct, ma? 1, 2, 3, 4, 5. Okay. What we have to do, ma? Tell me what we have to do. We need to group. So everyone knows the folding concept, right? Everyone knows the folding concept. So based on that, tell me the answer. So this one and this one you can group. Next is one. As we have one here, we can even go for this one and this one. Next is, if we have one here, then we can group as 4, but we don't have one here, so I have to combine this one only. Okay. Now we will find out the expression for X. I want an answer, ma. Let me give numberings for this. Okay. So let me take this one as 1, this one as 2, this one as 3. Tell me the expression for 1. First, is it for X, no? X, no? We are calculating for X output only, no?
Yes, ma'am.
Okay. So X equals to, so if you see in this 2, we'll be getting B
D,
and
C complement, D complement.
B, C complement, D complement, plus, if you see the second expression in this, we'll be getting B complement, and in this, we'll be getting D
D,
plus third expression, B complement,
C.
and
C.
C, B complement C. Okay. So listen all of you in the same way what we discussed in this case. So I'm writing B, C complement, D complement plus B complement I am taking common and I am writing D plus C. Now, as we have D plus C here, is there any way to convert this to D plus C? Yes. According to De Morgan's law, if it is A complement, B complement, it is converted to A complement into B complement is equals to, according to De Morgan's law, A complement into B complement equals to,
A plus B whole complement.
yes, very good. So it is A plus B whole complement. So in this case, what I can do, equals to B, okay, equals to B. So I can write this representation as C plus D whole complement plus B complement D plus C. Now, I will see who will substitute this one.
D XOR C plus D.
Yes, very good. So this is in the form of A B complement plus A complement B. So which is equals to, if the formula, if it is like this, A B complement plus A complement B, this is nothing but A XOR B. So what we have to write? B XOR with
XOR C plus D.
C plus D. So this is your final expression. This is your final expression. So see here, ma, don't keep it in your mind that if you do if you do this compression using a Boolean algebra, then only the answer will be correct. Even this is correct. What you got the expression x equals to, this is also correct, and even if you substitute the answer, this is also correct. So but the problem is, after substitution the number of gates will be reduced, but in this case the number of gates will be more. But what happens, the result is finally same, but initially the number of gates are more, but after simplification the number of gates are less. It is up to you. If you want to execute the application that you want to design, you want to execute very faster, then you need to reduce the number of gates so that the execution, there will be no delay. So why? Because for each and every gate there will be some delay. Given an input, it has to generate an output, then it has to give to the other gate as an input, it will generate an output. So there will be some delay for that. So execution will be a bit less, it will not be faster when compared to if the number of gates are less. So in this case, see here, can anyone tell me how many gates that we are using for this expression? How many gates we need
2
to use?
gates.
Two
Yes,
gates.
yes, we are using only 2 gates, but when coming to this, we are using so many gates here, plus plus, and we need to use AND gate like that. But the output from this is also same, and the output from this is also same. But the only difference is we are reducing the number of gates so that there is no delay, execution will be faster. Okay, so this is your final expression, B XORed with C plus D. B XORed with C plus D. Next. This completes your x expression. Then we'll go for, what's the next one, ma'am? What's next one?
Y.
Y equals to, tell me the values.
03478.
0, 3, 4, 7, 8. Okay. Now A, B, C, D, zero, 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 1, 1, 1, 1, 0. So 0 means you will be placing 1 here, you will be placing 0, 0, 1, 1 means 3, you will be placing here 0, 1, 0, 0, 1 here, 0, 1, triple 1, 7 here, 0, triple 1, 7 here, 8 is 1, this you will be getting 7, 8 here, and then 0, 3, 4, 7, 8, and remaining cases what we will be doing, and remaining cases we will be placing don't care. In which positions we need to place don't care?
Above
10
9.
to 15.
10 to 15. So this is your don't care. These are all don't care conditions. Now, what to group? What will be the expression?
C complement D complement plus CD.
Yes. So why? Because what we are doing here, we are grouping this one and we are grouping this one. Okay. So for this group, we will be getting y equals to C complement D complement plus CD. So which gate is this? Which gate is this first?
XOR.
Yes, it
XNOR
is. How to represent this?
C XOR D whole complement.
Okay. So we need to write okay. So this is your XNOR. Okay, this is your XNOR representation dot circle. Okay, which is also called as CD plus C complement D complement. Okay, so now the left out is we done with W, X, Y. The next one is what?
Z.
Z. Now tell me Z equals to?
D complement.
Good, D complement, but let me complete. Tell me the values. M of
0,
0,
2,
2, 4,
4,
6.
6,
0, 2, 4, 6,
6,
8.
8.
Okay, so this is your K map with 4 variable K map with inputs A, B, C, D, and we are finding the expression for output Y, for output Z. So this is your 4 variable K map with inputs A, B, C, D, and we are finding the expression for Z. So you will be having 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And for 0, we need to place 1 in for 2, for 4, for 6, for 8. And remaining cases, we need to place don't care. What is this, ma? 6 is there.
6 position is wrong.
6 position is wrong, no? Okay. 0, okay, it is for 7, no? 0, 1, 1, 1 is 7, okay. So I will erase. So 0, 1, 1, 0, this is your 6. So I'm placing here. And remaining all are don't cares. Okay. So in this, how many groups can we do, ma? 2 groups or 1 group?
1.
2.
1 group. That's what I have written. Maximum of the students will do what? This will be making 1 group and this. But I already said folding concept, right? Once if you fold, what happens? This corner one will become adjacent to each other. So we can group on 8. So we can group as 8. So if you group 8, all these will be cancelled. And among these two, which one is common? D is
D
common. So
complement.
finally, D complement is your answer. Z equals to D complement is your answer. Okay. Now let me go for logic diagram. Soon let me go for logic diagram. So I'm clearing. Before going for logic diagram, just tell me the expressions for W. W equals to W equals to what is the output
A
X?
plus BC plus BD.
A plus B C plus B D. We have written this as A plus B we have taken and we have written as C plus D. Next for X, for X,
B XOR
B
C plus
XOR C
D.
plus D.
D XOR C plus D. Okay. Next for Y,
C
C X
XOR
not.
D.
C X nor, sorry, it is C, no? Okay. C X nor D. Okay. For Z,
D complement.
D complement. Okay. So for all the inputs, we have 4 inputs. We know that A, B, C, D. In that only D we have a complement. So remaining all we will be writing as it is. A will be writing without any complement. B also will be writing without any complement. C also. But coming for D, we have to use the complement of that also. The complement of that. Okay. Next we'll start with the Z. Okay. Where is this? Z means directly I can give the complement of that. So this is your Z. Next is your Y. So Y equals to C X nor D. Tell me the symbol for X normal. Followed by, followed by, followed by. What is it? What I have?
A
Bubble.
circle.
Yes, yes, a circle. So for this input, one is C, and the other one is D. The other one is D. Okay, completed. Next, coming to X. X equals to D XOR C plus D. Okay, let me start
No,
with C.
ma'am. B XOR C plus D.
It is B, yeah? Okay, so where is this cursor? B, where is B XOR C plus D. So in this, I will start with C plus D. So this is your C, this is your D. Which gate I have to use? What gate is there in that? What gate is between C plus C and D? Plus is there, no? So for that, which gate I have to use?
Or gate.
OR gate. Okay. So OR gate. Next, the other one is B. Uh, one input is C plus D and the other input is B. Which gate I have to use then between these two?
XOR gate.
XOR gate. This is your X. Next is what? X is done. Next is W. W. So for W, the output is A plus B into C plus D. So C plus D already we got, right? So this is your C plus D, no? C, this is your C and this is your D. So we got C plus D here. I can take from this as one input C plus D and the other input is what? Other input is what?
A
B.
plus B.
Yes, A plus B, but let me complete this one. So C plus D I have considered from this output. The other operand is what? B. In between, what is there here?
AND gate.
AND gate. So select B, one more operand from this. This is your B. Select. And in between this, there is an AND completed and we got this. And next, we need to select what? A. So where is A? So this here is A. For this to, what I have to take? For this to A OR gate. So I have to select OR gate. So finally, this is your output. Okay. So this is the one logic circuit where given a BCD number, you are converting to XS3 code. Once it is completed, don't consider that your task is over. You now given a BCD, whether it is converting to XS3 code or not, let me check. So it is 0 0 0 0. Okay, now tell me, if it is 0, the output from this not is what? 1. So you will be getting 1. Now the you will be giving input 0 0. What is XNOR output? If it is 0 0, is it 1 or 0?
1.
1. So you will be getting 1 here. Next, 0 0. Why I'm blindly writing 0 means the input that I have given is 0. So there is no need of checking. By default, all inputs will be 0. So 0 0, you will be getting 0. From this, you will be getting 0. And finally, the output will be 0. So in this case also 0 0. For AND gate, if it is 0 0, it will be 0. And A is also 0. It is 0. So it is nothing but. So we need to take from this as WXYZ. Okay. 0 0 1 1. Is it converted to XS3 code?
Yes, ma'am.
Yes. Given a BCD number 0 0 0 0, it is converting to 0 0 1 1. Yes. This circuit, what we designed is working as BCD2. What we designed is working as BCD2 XS3 code. BCD2 XS3 code. Okay. So see here. This is the diagram that we have done, B3 plus B2, and we have considered common B1 plus B0. This is your diagram. But I already said that without Boolean algebra simplification also we can do. So this is the one where the exact output of this is the output what we have considered for this logic diagram. So we have not done any simplification for this expression. Here, whatever it is there for that expression, we have written what? The logic diagram. Okay, in this way also we can represent. That's the reason that don't confuse. This is a one which is there. So even in this way also you can write. In this way also we can write. And see here ma, how after simplification how many gates we are using in this? Total 5, let us suppose. But in this how many gates we used? More than 5. Means which one will be efficient? Which one will be efficient? The first one without simplification or the second one after simplification? Which one will be efficient, ma?
After simplification.
Yes. But don't consider that definitely we need to go for simplification. It is upon you. Even this is also correct. Even this also you will get maximum marks. Okay. So, but internally there will be some delay. But for this circuit, there will not be any delay. It will be executed